Hello everyone, my name is Daniel and I'm a programmer and an artist, and today I want to talk about indexes. I guess a good place to start would be to define what an index is. So if you have a list of things, in this case maybe the vertices in your mesh, then you have the first thing in the list and the second thing in the list and the third thing in the list. And that number, the first, the second, whatever, that number is the index of the thing in the list. And that index is useful because it's different for every single vertex in the mesh, and we can then turn that into some value that we can use to manipulate the mesh in some way differently per vertex. As a first example of how you can use the index to do something different to each vertex, I have this line here, and it has 11 points in it, and the index of those starts at 0 and goes up to 10. If we were then to divide the index by the number of points in the line, we'll get a value that instead goes from 0 up to 1. And then we can add more points to the line, and it will always go from 0 to 1. Currently, I'm just using that 0 to 1 value as the input to the x component of a combine XYZ node, and then we're scaling that by some value to make the 0 to 1 go to 0 to 5 for the x position of each vertex. If we wanted to do a little bit more with that, we could also plug it into the y component. That would give us a diagonal line that goes from 0, 0 up to 1, 1. And then if we're instead to run that value through some function, so in this case we could put it through a power node, that would allow us to curve the line in one direction or the other. So then you could imagine you could put any function you could come up with in between your 0 to 1 input to your combine XYZ node. For example, you could put a float curve in here. And then you could make whatever shape you wanted, like this, and you could apply that to your curve. And it's all dynamic. You can change how many points are in the curve and increase the resolution and stuff. So that's probably the first and most straightforward example of how you can use the index. You can convert the index into a 0 to 1 value, and then use that 0 to 1 value, running it through some math operations to create like a coordinate for that point to be placed at or something. Note this is also essentially what we did in the last video with the selections when we made the checkerboard pattern, where we did the index modulo 2 as the selection. So it can be applied to the set position node in this case, or a selection for the set material node. Lots of different ways you can use the index to do things where you do just some math on the index to get a selection. As another example of something you can do by doing some math on the index is you can take that one-dimensional array of numbers that increment by 1 and convert it into a two-dimensional array. So you could make something like a tile floor or a tiling pattern. So if you have an array of 20 items with indexes that go from 0 to 19, and you want to arrange those items into a 5x4 grid like this, then you're going to need to know an x-coordinate and a y-coordinate for each item. And those coordinates would look like this. So you'd have your x-coordinate goes from 0 to 4 for each row, and your y-coordinate goes from 0 to 3 for each column. And the way you can do that, the way you can calculate that value, starting with this 0 to 19 index, is by dividing the index by the number of elements in the x direction, so 5, and then flooring that so you can convert it to an integer and get rid of any decimal remainder, and then taking that same index and moduloing it by the x size so that you only keep the remainder. So then the remainder that you get by the modulo becomes your x coordinate, and the result of the floored division is your y coordinate. And you can see that here, 0 to 4, 0 to 3. So if you plug those two values into a combine XYZ node, then you can use that as an offset for set position. Or if a size of 1 is wrong because your thing is bigger, then you could run that through a scale node as well to choose what the spacing needs to be between the elements. Now both of those examples basically just use the index as it's available to us at that point in time in the calculation. But oftentimes it's useful to know about indexes that were previously true but are no longer valid. And to do that, we have to capture the index as an attribute. And the reason we have to do that is because a lot of the green geometry nodes can change the order or add or remove indexes from your list. And these are some of the nodes that do that. It's basically going to be any node that would add a point or remove a point from the mesh. So that's your delete and your separate or your join, Boolean, realizing instances, resampling curves, all of those are adding or removing points from your geometry. So what do I mean when I say it's useful to be able to capture an index that was previously true but no longer is? So here I have an example. I have this grid. It has 4 quads in it. And we have the index here, and we can see that the index is currently 0, 1, 2, 3, up to 8. And we can capture that index on the mesh, and those are currently identical. But then what we could do is we could go and we could make that geometry an instance, make a bunch of copies of it, and then realize those. Now you can see we have a whole bunch of geometry in our mesh. And if we look at the index now, the first one's the same. It starts at 0 and goes up to 8. But then the second one continues with 9 and goes up to 17, and so on. But since we previously captured the index, which was true back here when we only had one object or one instance in our mesh, we still have access to this pattern on every single instance that goes from 0 to 8, and that looks like this. And then we also have, because we use the duplicate elements node, the duplicate index, which will be the same for every single vertex in that particular instance. And so all of those different indexes could be useful for arranging these instances or the vertices in them in different ways. But I guess the main thing I want you to take away is when you capture an index is very important, and capturing indexes at different points through sort of building up your geometry as you're duplicating things can be very useful, especially when you're working with sort of arrays or building individual faces and stuff of a mesh. So here I have a little bit crazier example. This is looking at making a duplicate of some element for every single vertex in another mesh, and then sampling that mesh to get a position. So what we have here is we just have, as an input geometry, we have an edge. And that edge has vertices with indices, and they start at 0 and go up to 15. And then I also have a mesh line that just has 2 points in it. Those are obviously 0 and 1. And we can capture that index on that line at that point so that we have access to it later after we duplicate a bunch of them, where we make one duplicate for every point in the input mesh using the domain size to get that. So now you can see we have 18 edges to match the 18 points in this input geometry. So then I want to set the position of these elements to be along our input geometry, one at each vertex. And so the way we can do that is we can take the duplicate index, which is going to have the same count as our point count because we use the point count to make the duplicates. And we can sample the index of the vertex, the point in our input geometry, at the index of the duplicate to get the position of each vertex in our input curve, and use that as the position of a set position node. And then we can add an offset to that, which will just be a random vector, but only when the index of our original line before we duplicated it is equal to 1. So that is here. We won't move this 0 vertex on all of them because we want that to be on the curve of our input geometry. But if the index equals 1, then we will move it to a random offset. So then if we look at our indexes, if we look at our captured index that we captured over here, we can see it's 0 and 1 still for all of them, and 0 is along our input curve, and 1 got pushed off in some random direction. And then if we look at our duplicate index, you can see that starts at 0 and goes up, matching the index of our input curve. And altogether, that gives us this sort of craziness. So just to recap, we have a single edge with 2 vertices, and we capture those so that even after we make a bunch of copies, there's still only 0 and 1 on every single edge. And then we set the 0 vertex of each of those edges to match the position of a point in the input line, where the index matches the duplicate index of each of our copies. Now another thing that might happen is you could have a input geometry where you have a bunch of different objects where the number of vertices in each object is different, but you might want to create an index per object. And depending on what your criteria for doing that is, you can sometimes accomplish it with the accumulate field node. So say your criteria is that you want a set of indices for each mesh island. So for each mesh island, it starts at 0 and counts up to however many things are in that island. Well, you can do that with the accumulate field node, and I would call this sort of like custom indexes. So we can see here I have this input mesh, I have a cube, an icosphere, and a torus. And if we look at the standard index, we can see it starts at 0 here on the cube and goes up to 80 something on the torus. But then one of the input nodes that we have is the mesh island node, and it'll give us a different value for each set of connected vertices in the mesh. So if we look at that, we have 0, 1, and 2, because all of these meshes are different. And if we were to take part of this mesh here and separate it, we'd get another number over there. So then if we wanted to create a custom index that started at 0 or 1 for each mesh island and then count it up, we can do that with the accumulate field node by just plugging that island index into the group ID. And that'll give us this custom index where you can see it starts at 1 here on the cube, starts at 1 here on the icosphere, starts at 1 here on this part of the torus. So that's kind of like recreating from scratch the index that in the previous examples we captured before duplicating the object. But in this case, obviously it works even though the objects are different sizes with different numbers of vertices in them. Then there's a couple other cool things you can do with that. If you have that custom index and then you compare it to 1, because when you do the accumulate field, it starts at 1 instead of 0. If you want it to start at 0, you can subtract 1 from it, but usually it's not necessary. Anyway, if that custom index equals 1, then you'll get a Boolean value that selects the first vertex of each mesh island. And then if you multiply this original index times that Boolean value, it'll remove all of the indexes except the first one in each mesh island. And if you do a second accumulate field, where you accumulate the result of that multiplication, and you take the total, you can get the starting index for that mesh island in the combined mesh on every single vertex in that mesh island, if that makes sense. Another thing that you can do with this is when you have that Boolean value where the first index equals 1, if you take the opposite of it, you can delete all of those points and you end up with only 1 point left from each mesh island, which means that you can actually sample these points using the mesh island index. So that's essentially, if we were talking in programming terms, would be like creating a lookup table for the mesh island index out of your original mesh. Now that's not really necessary because when you accumulate the value to all of the vertices, that kind of does the same thing, and then it's saved in the geometry rather than having to sample it off of this sort of lookup geometry that you would create otherwise. But another trick that I've used a couple times. Now another thing you might want to do is randomize the indexes of some points. So you can see we have the circle here and the indexes start at 0 and go counterclockwise up to 15 in a very organized way. Now one way you could try to do this is with a random value node, and that sort of works, but you will get some numbers twice. So you can see 12 is in here 3 times. If instead you wanted to reuse the exact same indices of the original, 0 through 15, but just put them in different places, how could you do that? And the way you can do that is by first capturing the index, so that it becomes an attribute that's a value on the vertex, and then separating the geometry and joining it back together multiple times, just using a random value as the condition to separate it. And if you do that several times, then when you come out the end, you will have shuffled your vertices around. Now, you probably would have to do this a lot of times, or the more vertices you have in your mesh, the more times you might have to do this to get like a good mix. I haven't really tested that out, but it's the only way I've come up with to randomize the indices without having duplicate indices. And then when you come out the end here, you just sample the index that you captured, the value we captured back here, that was the index, and at the index, and transfer it from this shuffle geometry back onto the original geometry. And that gives us these random indexes, and you can see none of the numbers are duplicated. So then what we could do with that, for example, is to rearrange the path that these edges take through the points. So whereas here we have an edge that goes from 0 to 1, on this random one we could have an edge that goes from 0 to 1. And we could do that like this. And then you could join it back together and get some crazy pattern. So then once again, I wanted to end it with a little bit more of a thought out example. So here I've made an array node, but it's an array node where you're arraying things in a collection, and the size of each thing in the collection could be a different size. So I have this collection here, it has 2 objects in it, it has a little cylinder and then this cube, and we want to turn that into an array like this, where the cubes are placed 2 meters apart and the cylinders are placed 1 meter apart. So how could we do that? Well, first, for each object in our collection, we need to know how big it is. And we can do that using the indexes of a bounding box, So first we'll convert our input instances into bounding boxes. And then I just have some previews for that, so we can see that we have an instance index on each of those bounding boxes. So the cube is the first instance, and then the cylinder is the second instance. And then we have indexes for all of the vertices in those bounding boxes. So that starts at 0 and goes up to 15. So then what we want to know is the position of the vertices on opposite corners of the bounding box. And we can see that those could be the vertices at positions at index 0 and index 7. And we can also see that all of the numbers in the first instance are lower than the numbers in the second instance. So we could say that a bounding box is going to be 8 consecutive numbers starting at some value and then increasing by 1. And we can also say that because a bounding box is going to have 8 vertices in it, that the starting index of a single bounding box will always be divisible by 8. The first one will start at 0, the second one will start at 8, etc. So if we have our instance index and we multiply that times 8, that will be the position of the first vertex we want to look at. And then if we take that starting index and we add 7 more to it, we'll get the position of the second index we want to look at. So our minimum index is going to be 0 and 8, and our maximum index will be 7 and 15. And if we look at the vertex index, we can see that that matches up, 0, 7, 8, 15. So then we can sample the position off of our bounding box geometry at the indexes for the minimum and the maximum. And if we subtract those from each other, we can get a vector that goes from this corner to this corner, and we can measure how long that is. In this case, because I'm going to array it along the x-axis, I'm just separating it and taking the x component of that vector and capturing that on each instance. So now before we make a bunch of copies of these instances to array along the x-axis, we want to capture some information on them. And so the first thing we want to capture is just the index of the instance. So we have 0 for the cube and 1 for the cylinder. And then we have that size we just calculated. We want to know that. So we know that the cube is 2 meters in size and the cylinder is 1 meter in size on the x-axis. And then we also want to calculate a custom index. So we have our instance index here, and we pass that into accumulate field node as the group and accumulate the value 1. And if we look at the leading value of that, we have an index now for each object that starts at 1, goes up to 8 for the cube, and starts at 1 here, and goes up to 16, I guess, for the cylinder. And that's useful because the actual vertex index, if you just took the index input node, starts at 0, goes up to 7 for the cube, and then continues with 8 for the cylinder. But we don't know how many vertices the second instance might have in it, so we can't just calculate it some way based off of this index input. So then if we capture all of that information, so we capture the instance index, and we capture the size on the instance, then we realize the geometry, and we capture a custom index on that geometry that's based off of the accumulate field node, grouped by the first index we captured when it was still an instance. So again, notice it's important when we captures. Here we're captured, there's only 2 things and they're instances. We realize the instances, now we have a bunch of vertices, but we still can read the value that we captured when it was an instance. So then what we want to do is we want to convert that geometry into an instance so that we can duplicate that instance a bunch of times using the duplicate elements node. That gives us a new value, the duplicate index, that we can see here. So now you can see this first set of the collection has a duplicate index of 0, the second one of 1, and so on. Then we want it for each of those copies of the collection, we want to delete everything that's not one of the items. So we want to pick either the cube or the cylinder randomly for each iteration of the array. So the way we can do that is we can pick a random value between 0 and 1, where we use the duplicate index as the ID. So that gives us a value that we can use to delete by. So we can see the first 3 here were assigned the value of 1, and then the next 2 were assigned the value of 0. So then what we can do is delete all of the geometry whose instance index does not equal the delete key. You can see that looks like here. So for the first 3, we kept the cube, and then the second 2, we kept the cylinder. Then we still have access to the size attribute that we captured, that we calculated from the bounding box. But we can't simply multiply the size times the array index like we did with the earlier array example, because the sizes are different and all of the cylinders we get out of sync with the cubes, basically. So instead what we have to do is figure out which one we selected and add its size to a tally that we accumulate as we proceed down the array. We can do that with an accumulate field node and put that into the x-axis of a combine xyz node that becomes the offset for a set position to make the array. Now we can't just accumulate the value directly because it will add for each vertex. So you can see it starts 2, 4, 6, 8 on this first cube here. Whereas instead we want it to be 2 for the entirety of this cube and then only increase when we get to the next instance, which is the cylinder. So the way we can do that is by using the custom index that we calculated and making a Boolean value that's true only when the index equals 1, which is the first index in that instance. And then if we use this Boolean value and multiply that times the size, we'll get this result here, where the first vertex in each instance has the size on it, and all of the other vertices got set to 0 because they were false. So then if we accumulate that value instead, we can see that it starts at 2. When we go to the second instance, it gets the first vertex and adds the size that's still on that first vertex, which gets us to 3, but then the rest of that instance adds 0. And then we get to the first vertex of the third instance, the size gets added, and then the rest of the vertices add 0, and so on. And then now we have the value that's the offset for how far we need to move each object along the x-axis to make a perfect array with their different sizes. And that looks like this. Now we can see that that actually works because if we edit the cylinder and scale it, then it will resize to fit whatever it needs to be. So that's what I came up with to say about indexes. I feel like I barely scratched the surface, and I'm afraid it was kind of confusing. Hopefully it wasn't, but hopefully it was interesting, and feel free to ask if you have any questions about it. Other than that, that's all I've got for this one. Thanks for watching.